Tonight, your phone vibrates with an emergency alert. It does not tell you to evacuate. It tells you that every nuclear weapon on Earth has detonated on the same day. But the real answer is far stranger than one giant explosion swallowing the planet. Because nuclear weapons are not piled together in one place, waiting for one switch. They are scattered across military bases, submarines, airfields, storage sites, and missile fields. Some are ready for immediate use, some are stored, some are retired and waiting to be dismantled. If every one of them exploded, the world would not end in one cinematic flash. It would end in waves, and then it would keep changing for years. You would first notice the light, not everywhere. Only if you were close enough to one of the detonations, where the flash would arrive before your brain could understand what it meant. Near a nuclear blast, the immediate dangers are brutal and local. Heat, a pressure wave, fires, radiation, and collapsing buildings. But distance changes everything. A person far from a target might hear nothing for hours. They might see ordinary traffic, ordinary clouds, ordinary people checking their phones. The same day could feel completely different just a few hundred kilometers away. That unevenness matters. The world's nuclear arsenal is not evenly distributed either. The Stockholm International Peace Research Institute estimated that the global inventory was a little over 12,000 warheads in early 2025, with roughly 9,000 in military stockpiles for potential use. The United States and Russia hold the overwhelming majority. That does not mean every weapon is the same size or that everyone would produce the same result. A nuclear weapon is not a single thing. Its destructive power, location, altitude of detonation, weather, nearby fuel, and the density of the surrounding city would all shape what happened next. So imagine the impossible premise. Every warhead detonates where it happens to be. Some erupt near cities, some in remote missile fields, some at air bases, some beneath the ocean on submarines, some in storage facilities. The first hour is not one event. It is thousands of catastrophes sharing a date. Would the whole planet crack apart? No. Earth has absorbed impacts and volcanic eruptions vastly greater than the combined explosive energy of today's nuclear arsenal. The planet would survive. The question is whether human civilization could keep functioning on it. The first problem would be maps. Modern life depends on invisible systems spread over enormous distances. Electricity moves through grids. Food moves through ports, warehouses, rail lines, roads, and fuel depots. Money moves through data centers and communications cables. Hospitals depend on power, clean water, staff, medicine, and transport. A nuclear detonation does not need to strike every building to break a system. It only needs to break enough of the connecting pieces. You already know this instinctively. When a storm knocks out power in one area, you notice how quickly ordinary habits become complicated. The lift stops. The shop cannot take payment. The water pump may fail. The traffic lights go dark. Now multiply that not by the size of one storm, but by many regions losing critical infrastructure at once, while smoke, fallout, mass displacement, and panic make repairs harder. The first days would be defined by uncertainty. In places directly hit, emergency services would be overwhelmed immediately. In places untouched by blast waves, people would still rush for fuel, bottled water, medicine, and news. Governments would try to establish what had happened, which systems still worked, and whether more attacks were coming. In this hypothetical, there are no more weapons left to launch. But people would not know that at first. That fear would become a force of its own. Then comes fallout. Fallout is radioactive material made when a blast pulls soil, dust, building fragments, and weapon debris high into the air. Some of it falls close to the explosion. Some travels farther, carried by wind and rain. The exact pattern would depend on where and how each weapon detonated. This is why there is no honest single map of a global nuclear event. Weather would redraw the danger zone hour by hour. You might be hundreds of kilometers from a blast and still face contaminated rain, or you might be closer and safer because the wind carried the plume away. That is one of the most disturbing features of radiation risk. It does not behave like a monster you can see coming. It is measured, modeled, and mapped. It makes boring details, wind direction, shelter quality, time indoors, water supply, suddenly matter more than almost anything else. But the direct explosions and fallout are only the beginning. The greater global danger would come from fire. Nuclear weapons aimed at or near cities could ignite enormous fires in buildings, fuel stores, vehicles, plastics, forests, and industrial areas. Fire does not need a nuclear reaction to become planetary. It needs fuel, oxygen, and enough heat to spread faster than people can stop it. The smoke from those fires is the bridge between a local blast and a global crisis. This is where the phrase nuclear winter comes from. It does not mean snow begins falling the next morning. It means dark smoke, especially black carbon or soot, could rise high into the atmosphere and block or absorb sunlight. Alan Robach and colleagues used modern climate models to study how smoke from nuclear war firestorms could cool the planet and disrupt rainfall. Their work revived an unsettling idea from the Cold War. The largest danger may not stop at the borders of the countries fighting. The key word is smoke, not radiation. Radiation is terrifying, but it is not what would make farms fail on the other side of the world. Smoke is. If enough soot reached the stratosphere, the high, dry part of the atmosphere above most weather, it could remain there for years. NOAA researchers have observed powerful wildfire smoke plumes rise into the stratosphere and alter climate. Those observations do not prove every nuclear winter projection. They do show that smoke can climb much higher and persist much longer than everyday intuition suggests. Then sunlight weakens, temperatures fall, rain patterns shift, growing seasons shorten, and crops that depend on stable seasons begin failing in places that were never bombed. Lily Sia, Alan Robach, and their collaborators modeled food production consequences of several nuclear war scenarios in a 2022 Nature Food study. Their most severe scenario projected an extraordinary collapse in global calorie production after a large nuclear conflict. A model is not a prophecy. It is a way of asking what follows if the assumptions are true. But that question matters because food systems are already tight, connected, and dependent on predictable weather. Think about breakfast. Your bread may begin as grain grown in one region, processed in another, shipped by fuel from somewhere else, packaged in a factory, and bought with electricity. The supermarket shelf looks local. The system behind it is global. A climate shock does not have to destroy every farm. It only has to disrupt enough harvests, trade routes, fertilizer supplies, refrigeration networks, and political agreements that food stops moving where it is needed. At first, wealthy countries might try to protect their own supplies. That response would make the crisis worse. Food export restrictions, hoarding, and competition for grain would turn a harvest failure into a political cascade. Countries that import much of their food would be especially vulnerable. Cities would be vulnerable because they store only a limited amount of food inside their borders. You could have a field growing somewhere and still have people hungry because ports, roads, banking, or governments no longer work well enough to connect the field to the plate. Would everyone starve? No. People would adapt. Farmers would change crops. Communities would ration. Governments would redirect resources. Greenhouses, stored grain, fishing, local production, and emergency systems would matter enormously. But adaptation is not magic. It needs energy, coordination, time, and trust, the exact things a global catastrophe destroys first. The oceans would not simply save you either. Cooling and reduced sunlight would affect marine food chains, beginning with microscopic plankton. Plankton are tiny drifting organisms that support much of the ocean's life and help produce oxygen. Less sunlight can mean less photosynthesis, which means less food at the base of the sea. Some regions might see temporary opportunities as waters change, but the wider system would be stressed at the same time humans would depend on it more. Then there is the social shock. You tend to picture collapse as empty streets. Real collapse is often crowded. People move toward relatives, water, food, borders, and rumors of safety. Hospitals fill, roads fill. Governments face impossible choices about fuel, evacuation, security, and aid. Information becomes valuable, which means misinformation becomes valuable too. A false message about a safe route, a contaminated city, or a food depot could move thousands of people. This is where human psychology becomes part of the disaster. The late psychologist Stanley Milgram became famous for studying obedience, but his deeper lesson is that ordinary people are strongly shaped by the systems and authorities around them. In a crisis, you do not become a completely different creature. You become more dependent on cues. What officials say, what your neighbors do, what the crowd believes. Trust is infrastructure, just like a bridge or a power line. If trust holds, people organize shelters, share food, and protect each other. If it fails, every cue can become a conflict. Still, the world would not become equally dark everywhere. The southern hemisphere might experience different climate effects than the northern hemisphere. Remote agricultural areas might avoid direct strikes. Some electrical systems would survive, some governments would keep operating. Human beings are stubbornly good at rebuilding routines from scraps. That is the counterintuitive twist. The apocalypse would not be one final moment. It would be millions of people waking up each day inside a smaller, colder, more uncertain world and trying to make it work. A farmer chooses whether to plant a risky crop. A nurse chooses which patient gets limited medicine. A family decides whether to leave home. A community decides whether food is shared or guarded. Civilization does not disappear like a light switch. It becomes a series of difficult decisions made under pressure. And after the smoke begins to clear, another problem remains. The weapons may be gone, but the materials, damaged sites, contaminated land, lost expertise, and political trauma would stay. Rebuilding a bridge is hard. Rebuilding a world economy after simultaneous global disruption is harder. Rebuilding trust between countries that believed they were under attack may be hardest of all. This is why nuclear weapons are different from almost every other weapon. Their danger is not only what they destroy at the target. Their danger is that they can turn the systems supporting people far beyond the target into part of the blast radius. They make climate, agriculture, trade, health, and fear into weapons too. Tonight, your phone might vibrate with an emergency alert. It would not be telling you that the world had ended. It would be telling you that the world you took for granted was a system, and systems can burn long after the first flash is gone.